Hi and welcome. This time around is going to be a little bit different video than I've ever done before. Normally my videos are all about the machining process. This time around I was in a bit of a hurry and I already spent a couple days doing machining off and on. And so I didn't have time to shoot it because that makes things take about twice as long. This project is to make a davit, and a davit is basically a winch for a boat, and they can either be deck mounted or rail mounted. And in this case, for my brother-in-law, this one is designed to pull up crab and lobster cages. So we purchased this wheelchair motor, and there are two on a normal wheelchair that drive the wheels, and it's a 12-volt motor, pretty high torque. And this piece here is a cannon mount, and it fits in the side of the boat and mounts into holes that are already pre-done in the rails. If not, they have another kind that has another flat plate that mounts on the deck. But this is one that goes into the rail. So what we need to do in this project is we need to make a piece like this that will mount to the plate that goes in the rail right here. Then there's going to be a vertical pole that mounts into here. It's going to be ultimately welded in, but it needs to rotate. So there is a piece that fits down here, a small piece. In there will be press fit and a acetal bushing that I made, about a 1/4 inch thick all the way around. Then there'll be the stainless steel plug. And then the stainless steel plug will fit into the vertical piece here and will be screwed in. I still have to drill and tap that hole. Then this vertical piece here has a plate that slides in. I rounded off both top and bottom and milled a 1/4 inch slot in it. And the other end will attach over here on the motor housing, like so. There is a pulley which you wrap some 1/4 inch line around, and I put a recess. I made the pulley, put a recess in it so that this piece will seat a little bit into the pulley itself before you tighten the screws down. The hardware is all stainless steel. Unfortunately, all I had was 304. You really want 316 for ocean kind of in saltwater environments. The mount for the pulley wheel, figuring out the dimensions of this was a bit challenging, because if it's an even number of holes, then you just measure across 2 holes, subtract the diameter of one of the parts, which would be half, the equivalent of half for each side, and you've got the bolt circle diameter. However, with an odd number, these lines here are not diameters, they're chords. So you've got a chord here and a chord here, and a chord is just a line that goes through a circle but does not cut it in half. The diameter would be in the middle, would be a chord that runs down the middle, and a regular chord would be anything other than that. So any odd number of holes in a bolt circle, and all you get is chords. So the way I calculated the bolt circle diameter was take careful measurements of the chord lengths, go into my CAD, reproduce it with a little bit of geometry, and figure out what the bolt circle is. So I was able to do that, and we got these holes nice and matched. So I'm going to show the assembly of this, but I'm also going to show some of the complicated setups I had to do to figure out angles. So one of the things, the davit, is you don't want the post that sticks out. That will be welded. Hold on a second, let me grab this here. This guy will be welded over here, and you can see that it mates at what works out to be a 45 degree above 90 or 135 degree angle. And you don't want it straight to the side, so these will have to be welded together. And unfortunately, when my brother-in-law was trying to figure out dimensions, he cut these 22.5 degree angles first. And it's very important that the motor be lined up perfectly with this angle. So you'll notice the slot lines up with this angle. So you might be wondering, how do you do that with any kind of accuracy? And I'll show you the trick I used. Alrighty, so here's my piece that I need to line up. I want to line this end up, not this end, but this end, the slot needs to line up with the peak of this ellipse or the long axis. So how did I do that? Well, I did it by putting a flat parallel in the bottom, holding this guy flat on the parallel, and then tightening the jaws. But that may not be clear why that works, so let me show you. So picture this as an ellipse without the curved parts in it, this piece of stock here. So when I tighten the jaws, it naturally aligns the part so that it will be center line of the part will be dead center between the two jaws. Well, the same works for the ellipse, because it's a lot like in a rectangle. With it, you can actually draw an ellipse inside the rectangle. So what you do is you very carefully hold it flat to the parallel. Here, I'm going to put it at an angle. Although with ellipse you don't get as much torque trying to turn it, so but you see it's rotating it. So what you want to do is wiggle back and forth. Find out when it hits the peak. Okay. So once I got that, then what I did was I put a point center inside my quill, and I dropped the quill, which can always be a trick. I dropped the quill down and put a mark, just one mark right here at the bottom where I could reach it, because this is a pretty large diameter marking point. Once I got that marked, I just took this guy, took the parallel out since I didn't need it anymore. Just set this guy in here. Oh. Used my center finder, found the center between the two jaws. Once I was lined up on center between the two jaws, then it was just a matter of going back and forth until I got this guy, this point, to line up perfectly in this hole. Once it was lined up in the hole, and I did that by rotating the piece and then tightening the jaws. Once I got that, then I just went down the piece, put a few more marks until I got to the other end. And that ultimately gave me the points to line up with this guy. Now, I drilled 2 holes through this right off the bat, milled the slots, and I uncovered something kind of interesting. The milling cutter I used was long enough, although the cutting threads weren't long enough to reach the bottom, but I figured the shaft would be the same diameter as the cutting threads, or smaller. I think the shaft is just ever so slightly larger, or deflection in the bottom caused the top of the shaft to rub on the slot that was already drilled, or milled rather. And what ended up happening, which I took off with a file, was actually stirring. And it actually rubbed on the side of the aluminum slot enough to melt the aluminum, and I had a really roughed up texture on the whole top of my slot, which made one side slightly larger than the other after I cleaned it up, which was unfortunate. What I needed was a longer cutting flute end mill, which for 1/4 inch would make it kind of fragile, but I was taking small bites and that would have worked. I just didn't have one. So that was a lesson learned, that either deflection in the bottom or the fact that this isn't a 1/4 inch. What you really need is a reduced diameter shaft on the top so that it'll clear and won't rub when you're cutting the bottom slot. Okay, so next up, how do I get these guys perfect 90 degrees off? All right, so the next part of the project was to be able to drill perpendicular 90 holes at a specific spacing and parallel off of the side of this part. So I have the plate that goes through here that I machined before I drilled these holes, and I stuck it through here. And then I used some of this tooling plate. Now, tooling plate you can buy at your metal supplier, and it often comes with protective plastic on 2 sides because it's machined and ground to be very, very flat and parallel both sides. So this 1/2 inch plate is very, very close to 1/2 inch. It's really handy to have around because if you want some material stock that you can trust as being parallel and flat, this is a good way to go. So here is a 1/2 inch piece, and all I did was I slid this guy up, held this part over, and then drilled my 3 holes. And I could have clamped it, but I didn't need to because there's almost no cutting force. I just held it in place while I drilled. So that's how I got the holes perpendicular, because since this plate's going through the middle, it's pretty darn close to perpendicular, except for the small fact that I made one side slightly larger than the other accidentally, which made this not perfectly perpendicular, but perfect is not a requirement here, fortunately, because of my screw up. Okay, I also took all the poles to the lathe and made them their 1/4 inch wall, and I machined out the inside, and they're normally 1 1/2. nominal, and they were around 1.498. I made them 1.525 so I could get a good cleanup pass, and I did that with all surfaces where I'm going to be mating with. That way I got a inline, parallel to the axis surface to work with. Now, my lathe actually supports up to, I think, 2 5/8 going through the headstock. For people with smaller lathes, that's going to be a little more challenging and problematic, so you might have to look for another solution. In case you didn't notice, this plate here is sitting on a couple of parallels. So to get dimensions on the motor plate, mounting plate, since obviously it didn't come with any, it was fortunate that these holes are fairly accurately machined, and so spacing was pretty easy because I grabbed some 3/8 inch dowel pins. Always handy to have a selection of them. Measure side to side, take away 1 diameter, and that gives you the center to center. Same thing with this one. This one's a little bit looser, but I was still able to do it. It doesn't fall through, fortunately. As for front back location, I used a depth mic. It's got a larger surface than the tail of the calipers do, so the chance of hitting the peak of the diameter is much higher. So I measured that distance. I measured all the way to the back. You can subtract the diameter to find the center again. Also from the sides, I also used the depth mic. Turns out that these, even this one and this one, are not symmetrically located. From here to here is 4 inches. This is 2.5 even, but this is like 0.6 something to the center, and this is like, or 0.7 something to the center. This is 0.6 something to the center. Why they did that, who knows? But once I had those dimensions, I was able to drill out this plate, and I got really good alignment. Next, let's head on to assembly. Starting on assembly, we'll start with the motor housing, and I can take the pins out. And again, I double radius the sides of this to match up with the slots on the pole that it's going to be mounted to. But I had to radius 1/2 of the side to make the motor mounting plate fit flush because it's radiused. So here is a straight edge, won't mate up. So 1/8 inch radius, used my radius gauge, my stair radius gauge, and was able to find those dimensions. And then it's just a matter of popping 3 screws in there. Next, with the motor plate mounted, then I can put the pulley on, because you put the pulley on first, you can't get to 2 of the bolts very easily, so it's better order to go in. One side of it is recessed a little bit more than the other and fits right over the pulley. I replaced the hardware that came with the motor, which was just black oxide coated. This is going to be in a marine environment, so I replaced these with stainless. Again, I would have liked to have 316, but 3/16, but they didn't have any, so I had to go with what they had, which was 304, which is 18/8. Next up, you can mount the pole. All right, now that I got the motor housing here, I can pop this guy, and I want the loose side towards the motor housing and the tighter side in the back. And what I did for these is I used, we wanted this to be removable so that this part would be mounted on the deck and you could take the heavy motor off by itself. And so I went with bolts, washers, and 3 wing nuts. Okay, now next in the end of this goes this stainless steel piece. I still need to drill and tap through here to make this stainless steel piece fixed in the end. Then this bushing will be press fit into this bottom part of the tubing. But first, the bottom part of the tubing is going to get welded into here. And that will be all of your strength. And I made this go down quite far so that it was additional strength from wanting to tip over, but it should rotate very easily. I will also need to drill through this guy and through the pin and through the bushing with a pin all the way through to lock it 90 degrees when you're using it. I don't want to press fit this bushing because it's pretty tight right now, and I still need to weld this. This guy mounts to the Davit mount through these outside 4 holes, drilled and tapped here. Again, using a pin method to find the locations of the holes, and we are good to go there. So what I have left to do on the project is some welding right here. Drill and tap this stainless steel piece that I made. And then I've got, of course, I have to weld. I don't know if you can see this. I have to weld these pieces together. Add a support bracket down right here, because I don't think this is going to be strong enough all by itself. It might be, but we're going to add a piece of material we're going to weld on right there. And then on the end here, I'm going to make a cap, and we've got to make a hole for the pulley to hang off of it. And after that, the Davit should be complete. My brother-in-law is handling the wiring to the 12-volt motor and the switch, the high current switch. This motor draws anywhere as much as 40 amps under full load, peak load. As a result, you need to be very careful how you do the wiring on the boat. It's got to be fused and go straight to the battery, and it's got to have a very heavy-duty switch, or you'll just wipe out the contacts. So also, you need to probably have your motor running while you're using it, because the motor, like my brother-in-law's outboard motor, is a 350 horsepower, and it generates about 75 amps of current. This could potentially take 40 of those. You don't want to wipe your battery out. You could wipe your battery out pretty quickly at a 40 amp draw. So even 25-30 is a lot for one of those batteries to be continuous. So that's pretty much it. I'm going to bring you back for a couple snapshots after I get to the end here. I've just got a little, like I told you, a little bit more to do, and I'll bring you back. All right, here's 90% of the way done. Just need to drill a hole in the top, put an eye bolt in for the pulley to hang on just off the top up there. But right now it's mostly done. We have it sitting in the vise, but it's so heavy that if you don't support the bottom of it, it does spin really easily, but this is where it's normally going to hang, like this. But the vise won't hold it in place, and I don't want to crank it enough to crush the shaft. So I need to wait over there. Actually, at this point right here, I could slide this pin in and lock it in place. We're going to need to get something to make that captive when we're done, like a piece of stainless steel cable. Pulley's all good in place. Don't make fun of my welding job, but 1/4-inch plate supporting this. This is 1/4-inch thick tubing, so pretty beefy. There will be the hole in here for the pulley, as I just said, and we're good to go. With all the weight in this thing very, very easily spins, which is handy. So this is it. So the way this will work is the rope will come out of the water, come up over the pulley, come down, and loop over the pulley once, maybe twice, and then you will by hand draw the rope, and this is basically a torque assist. So that is the plan, and again, the electrical my brother-in-law is going to handle when he gets to the boat side. Anyways, that's it. Thanks for watching. Hope you find it useful. Hope to see you next time.